By the end of this lesson, you will be able to find the number of degrees in a polygon, as long as it's not convex, on the interior, which are interior angles, the number of degrees on the exterior, and if we have a regular polygon, how many degrees are in each exterior and each interior angle. So a polygon is a simple closed figure. It has at least 3 sides on the and it has vertices. And we're going to talk about ones that are convex. So they can have any shape, but not ones that are concave. Okay? So concave, we're not talking about ones that go in like that. So that what we talk about today only works for ones that are convex and not concave. There's some polygons that you need to know the names of. Triangles, which you should already know, that's 3-sided. Quadrilateral is 4. Pentagon is 5. Hexagon 6. Heptagon 7. Octagon 8. Nonagon 9. And decagon 10. And there's one more. 12 is dodecagon. Okay. And the first thing we want to talk about is how many degrees are on the interior of a polygon. Again, a convex polygon, not a concave. Okay, if it goes in on itself, concave, then these don't work. And what we can do is we can split a polygon into its number of triangles, and it's the number of triangles times 180 degrees, because there's 180 degrees in a triangle. So let's draw a quadrilateral and a pentagon. We'll draw a hexagon. Okay. And let's draw some diagonals on it from one vertex. So we'll pick a vertex and draw a diagonal. And you notice this splits this into 2 triangles. 2 times 180 is 360. This works for all quadrilaterals. All quadrilaterals have 360 degrees. Pick a vertex on the pentagon. There's 1 and 2. Whoops, that did not work. And there's the other diagonal. That's split into 1, 2, 3 triangles. So 3 times 180, 540 degrees. Pick a vertex in the hexagon. 1, 2, 3 diagonals. And so it's 1, 2, 3, 4 triangles. So 4 times 180, which equals. All right, let's see if we can see a pattern here. So, and we'll try to see if this pattern works for an octagon. So let's see if we can draw an octagon. 1, 2, 3, 4, 5, 6, 7, 8. Oh my gosh, it's a miracle I drew one. All right, so 4 sides, 2 triangles, 5 sides, 3 triangles, and then 6 sides, had 4 triangles. So how many triangles do we think an 8-sided figure would have? Well, if I'm looking at the pattern, the number of triangles is always 2 less than the number of sides. So 4 had 2 triangles, 5 minus 2 was 3 triangles, 6 minus 2 is 4 triangles. So we want to see, this should have then 6 triangles. All right, so we're going to pick a point. Let's draw the triangles. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, just like we thought. And then 6 times 180, this octagon has 1080 degrees in it. Okay, and that's true for all octagons, again, as long as they're not concave. Then we're talking the number of degrees switches. So, if we put that into a formula, if a polygon has n sides, then n minus 2 triangles are formed. So the sum of the degree measures of the interior angles of a polygon is n minus 2 times 180. So you don't have to draw a triangle every time, but you can't, or a polygon every time. You can, but if you have like number 6, a 35-gon, or a polygon with 35 sides, it gets rather difficult. So decagon has 10 sides. So we solved that. The number of triangles is 10 minus 2 times 180, which is 8 times 180, which is 1,440 degrees in a decagon. So again, you don't have to have any of the degrees memorized. You just need to know how many degrees there are in a triangle, and then you can apply that to any convex polygon. So 16-gon, 6 minus 2 times 180, which is 14 times 180, which is 2,520 degrees. A 30-gon, the number of triangles is 30 minus 2 times 180, 28 times 180, which is 5,040 degrees. That is a lot of degrees. Octagon, we just did that one. All right, 1080. A 12-gon or dodecagon, I think in your classwork I call it a dodecagon, is 12 minus 2 times 180, which is 10 times 180, which is 1,800 degrees. And finally, a 35-gon, which I don't think I could draw. It would look too much like a circle, which is 33 times 180, which is 5,940 degrees. So it's the number of triangles times 180, and the number of triangles is always 2 less than the number of sides. Now I want to talk about the number of degrees on the exterior. So this is what I mean by exterior. So let's say we have a hexagon. And again, all the sides do not have to be the same. Okay. What I mean by exterior angles is if I extend the sides, what would all the, now I know it looks like I'm marking congruent, but I'm just making marks on those. Those are not congruent angles. All right. What would those have to add up to? Now, what's kind of neat about it, if we went and we connected all those lines together, all right, and kind of squeezed it, kind of like in the James Bond movies when you're looking like down the barrel, and it's kind of like, and it kind of closes in on you. If I connect all of these lines, they're going to meet in the middle. All right, if I kind of push all these lines together, they're going to meet in the middle. So let's see if I can do that. So they would kind of push all together. If I put all those angles together, they would actually meet in the middle and they would fit perfectly together. And if you go all the way around that, remember that's 360 degrees. So if I go around this polygon, I'll go 360 degrees, okay, because I'm going all the way around it. Now that doesn't work in the interior because we're making stops on the way. But what's cool is if I cut out all these angles, they would fit together perfectly in the middle, and then they would go around to 360 degrees. So the sum of the exterior angle measures of a convex polygon, remember this only works for convex, with one angle at each vertex, so I put one angle at each vertex, is 360 degrees. So the sum of the measures of the exterior angles of each convex polygon, this is 360 degrees. 16-gon, 360 degrees. 36-gon, 360 degrees. So they always add up to 360. It's really cool. And I know it sounds, you might not want to do it, but if you take some time and actually draw that and cut out those angles, you'll see they meet in the middle. It's really kind of neat. A regular polygon is a polygon that's equilateral, all the sides are congruent, and equiangular, all the angles are congruent. So if we go to draw like a square as an example of one, okay? So a square. A pentagon, if you draw it just right, and I didn't. Nope. Let's see if I can draw a regular hexagon. So same. Oh, I tried. Okay. Oh gosh, that's bad. So all the sides are congruent and all the angles are congruent. Okay, so they're all the same. Okay, so all congruent to another. So that means all the exterior angles would all be the same as well. So each exterior angle would be the same. So we could split it up into those equal pieces. So if I look at this, like that angle, that angle, that angle, that one, and that one are all congruent. So if we wanted to know, and this again only works for regular, if I have a shape that kind of looks like this, it's not going to work. All those angles are not congruent. If I want to find the measure of each exterior angle of this regular polygon, I just divide by the number of sides, because the number of sides is the same as the number of angles. So if it's a convex polygon, the number of sides and the number of vertices are the same. So a 12gon, if I want to know how many each, or dodecagon, if I want to know how many degrees are in each exterior angle, I take 360 and divide it by 12 evenly, and I get that they are each 30 degrees. For a hexagon, I would divide by 6, and I get each one is 60 degrees. If I do a 20gon, I'm going to divide by 360 and divide 360 by 20, and each one is 18 degrees. So each exterior angle is 18 degrees. If I wanted to find the measure of each interior angle, I have a couple of choices. Okay? I can put it into the formula. So the number of triangles, 5 minus 2 times 180, that's the total number of degrees in that pentagon, and divide by 5. All right, so 3 times 180 divided by 5, which is 540 divided by 5. All right, there's 540 degrees total in that polygon. Since it's regular, each angle is congruent. It's kind of like 180 degrees in an equilateral triangle, so each one's 60, because 180 divided by 3 is 160. If we're talking about a regular pentagon, the total number of degrees is 540. Divide that by 5, so each angle would be 108 degrees. The other way you can do this problem, and we get the same answer, is if we think of a regular pentagon. Oh geez, I'm going to try to draw one. Oh, I tried my best. If we look at the interior and the exterior, notice they are supplementary. Interior and exterior angles are always supplementary. Interior plus exterior always equals 180. Okay, so degree in the degree of the exterior always equals 180. We're talking about one angle. So what I could do is find the exterior of this. So I could say, hey, 360 degrees on the outside, divide that by 5, and I get each exterior angle is 72, and I could do 180 minus 72, and I get that that would be 108. So that's another way you could do that problem. So number 10, let's do it one way, and then number 11, let's do the other. So for number 10, we'll do a nonagon has 9 sides minus 2 times 180 divided by 9. 7 times 180 is 1,260 divided by 9. Each angle is 140 degrees on the inside. For a regular 18gon, we can do the other way. We can say, all right, 360, divide that by 18, each exterior angle is 20. So that means each interior angle is 180 minus 20, which is 160 degrees. It doesn't matter which way you do it, each way works. Now, they want the measure of an interior angle. Again, this only works for regular. Polygon is given. Find the number of sides. So now they're giving us, they're saying, hey, the interior angle here is 144, and it's regular. So what do the other degrees have to be? Again, what's kind of helpful, the easiest way to do this is to use the outside angle or the exterior angle to help us. So I'm going to do 180 minus 144. And that says this is my interior. Okay, if I subtract that, I get the exterior. And then I just say, all right, 360 divided by that, that'll tell me the number of sides, which is 10. Because there's always 360 degrees there's always 360 degrees on the exterior of a polygon. You can, if you want, you can always use this equation, n minus 2, number of sides, times 180, divided by the number of sides, equals 144. So you could solve that equation if you want to do it as well. That's another way of doing the problem, but I guarantee this way is a lot easier. So using the fact that interior and exterior add up to 180. So 180 minus 156 equals 24. 360 divided by 24, the number of sides is 15. So each interior angle is 156. It's a regular polygon, so each exterior angle is 24. Well, I said that wrong. That's not the reason why they're 24. Remember, they're always supplementary, even if they're not regular. So even if it's not a regular polygon, there still would be supplementary. But because it's a regular, I can divide 360 divided by 24, and that'll tell me the number of sides. Okay, so let's find the exterior of this one. Each exterior is 20, and since it's regular, it divides it into equal pieces. So that would have 18 sides. So the number of degrees in a polynomial on the interior is the number of triangles, or n minus 2 times 180. The exterior always add up to 360. Interior and exterior add up to 180. In a regular polygon, all the angles are congruent on the inside, or interior, and on the outside. So now what you're going to do is problems 1 through 8. 1 through 8, 11 through 16, and 4, 5, and 6. That's not too bad.